Johnson? Audio's good? Yeah. Okay, I'll start. Heavenly Father, we thank you for this morning. Thank you for these students. Pray to help us to have a good day today, to understand what Taylor series are, and just to enjoy the math we study. Lord, in your name I pray. Amen. So, go ahead and turn in your homework. I think it's time. So today I want to talk to you about a Taylor series. But really, Taylor, they are Taylor series, but I would say a better thing to say is we're looking at power series. That's what I usually call them. What is a power series? Definition. If f of x is equal to a naught plus a1 times x minus c plus a2 times x minus c squared plus a3 times x minus c cubed plus dot, dot, dot. In other words, the generic term is the sum, let's say k equals 0 to infinity of a sub k times x minus c to the k-fold power. This is said to be f of x is a power series centered at c with coefficients a naught, a1, a2, dot, 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 and so forth, right, in the reals. That's part of the definition. The coefficients have to be real numbers. C has to be a real number. Let me put this in another term. So what I'm saying is a power series, this is the viewpoint I'm taking today, okay? A power series is a function on the reals. It's a function from the real numbers to the real numbers for which the formula of f of x, the formula, let's say for f of x, is given by a series. Now, to be precise, it's given by the same series. How to say this? It is what it is, but at each point, it's given by a series, right? But the series that we're talking about, the ones at different values of x are related, right? The series that I calculate for one x and the series that I calculate for another x, they both have the same coefficients in the sense of the definition, right? Like, if I was to calculate, for example, f of 0, what would I get? So like f of 0 would be this series, right? What would f of 1 would be what? It'd be that series. There's one very special case. Now, what I just wrote may or may not be nonsense, actually, for a given power series. What I'm trying to say is, you said it's a function, right? In fact, okay, so I'm not. What I'm trying to say is my definition up here isn't quite done yet. All right. I'm just telling you it's a function, right? So what is it? What does a function have? It has a domain, right? So some domain for the function, right, to the reals, where the domain of f is all x such that the series f of x, well, to be more specific, the series a1, a0 plus a1 times x minus c plus a2 times x minus c squared plus dot, 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 converges. So like, I can talk about f of 0 and f of 1 down here, but for a given choice of coefficients, it may or may not even make sense to write f of 0 or f of 1. It could be that 0 and 1 are outside the domain of the given power series. All right? So I told you guys yesterday that power series are like unending polynomials, right? You guys asked me a question which brought it up, remember? But there's one big difference, right? What's the domain of polynomials? Reals, right? That's not a very interesting question. So he's like, what's the domain of this polynomial? And you're like, why don't you just give me points for writing my name? Like, it's the same, right? I mean, it's obvious, it's reals. This, on the other hand, is an interesting question. The domain of a power series doesn't have to be the whole reals. It's actually rather interesting, the domain of a power series, and it requires analysis. But there's one kind of uninteresting point for a power series, right? What happens when we plug in x equals to c? Yes. We get a0 plus 0 plus 0 plus 0 plus 0 plus 0. Well, you get the idea. The 0 series converges, right? That's true. No, it doesn't. I mean, what is a0? A0's a number. So this domain is never empty. There's always at least one point in the domain. What point is always in the domain? C is an element of the domain of f for f of x centered at C. So you always have at least that point in the domain of a power series. Okay? So let's look at some examples. How about this? F of x is equal to 1 plus x squared plus x cubed plus dot, 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 dot. What is that equal to? This is a geometric series, right? Geometric with what? Geometric. A equals to 1, r is equal to x, right? Multiply by x to get to the next term. The first term is 1. Geometric, so it's a over 1 minus r, right? Which is what? Very good. And that's true for what? All right. Let's try to understand this example a little bit more. Now, you're like, wait. I thought you said that, you notice that this is only true for that, right? The function is not defined by this formula. I'm saying the function is defined by this power series. That's important. This formula is a rational function. Its domain is everything except for 1, right? We could graph this thing independent of the power series. Let's do that. What's the graph of y equals 1 over 1 minus x look like? Well, that's really minus 1 over x minus 1, right? You've got a vertical asymptote at 1, right? And it's flipped over. So it's looks something like this, right? let's try to understand what's going on with this series. Where is this series centered? Yes, 0. So like x minus 0 squared. It's kind of stupid, but there it is. By the way, this is what's called a Maclaurin series. Series centered at zeros are called Maclaurin series. Now, so let's see here. If I was to draw it in red, right, the applicability is like from here, right, over to, let's see here. So we got 0, you got 1. Over here you got -1, right? So this power series is only modeling, it's only approximating the rational function -1 over x minus 1 on that little red piece, right? But if you're interested in the behavior of this rational function right here, you can use that power series to approximate how it behaves, right? Let's see here. So all my examples are kind of like this to start with. Let's see here. Well, actually, let me. So let's see here. This time, what was the domain of f, by the way? It was -1 to 1, right? So let me just skip ahead a bit. Well, actually, let's investigate the meaning of if there's not a question. Let's investigate the meaning of these coefficients. All right. So I want to show you why there's this thing called Taylor's theorem. That's why we're calling these Taylor series. And so let me see. Let's call this motivating discussion for. Taylor's theorem. So what's the connection between the coefficients here, like a naught through whatever, and the function that we're defining, right? It's like we have f of x is equal to a naught plus a1 times x minus c plus a2 times x minus c squared plus plus a sub let's say a sub n times x minus c to the n power and so forth, right? So you could say that f of x is equal to the sum. Let's see here. K equals 0 to n of a sub k times x minus c to the k power, right? And then what do? Take the limit, right? As n goes to infinity of that. What I just wrote in the parentheses is this is the nth Taylor polynomial. Well, I guess I'm confusing. Fine. All right. I need to kind of back up here a second. We need to think about another function which is given. All right. So suppose you're given a function, right? We need another name for it. What do you guys want to call it? Let's see. Suppose g of x is a given function, right? And what I want, and f of x equals to this, is to approximate. Well, not really approximate. That's probably the wrong word, is to reproduce reproduce g of x over some set of the real numbers containing c, right? Like we did over here, right? So like the idea, the concept I'm trying to get across to you guys is we're given some real function like this. Here's my g of x, right? I did this problem backwards. I started with the series, which we already know how to manipulate because we know geometric series, right? Technically speaking, since I'm thinking of x as a variable, it's not a single geometric series, right? It's a whole family of them, one for each x between -1 and 1, right? That's the distinction, right? Now we're thinking about not just one series, but a whole bunch of them, one for each x in the domain of this power series. But this is the quote-unquote f of x in my discussion over here, okay? Does that make sense, what I'm trying to set up? So you're given this g of x. You're trying to find a power series, f of x, which reproduces g of x. What can you say? The question is this. What can you say about the relation of the coefficients in your power series, f, and the given function g? What's the relation between the coefficients? So let me write that down. Question. What is the relation between a sub 0, a sub 1, a sub 2, and so forth, and the given g of x? Answering that question carefully is exactly what Taylor's theorem does. So you guys, can you guys tell me what a sub 0 should be as it relates to g? So g of c should be equal to f of c, right? But what is f of c? F of c is a sub 0, right? Aha. So therefore, a sub 0 is equal to g of c. Now, g is a given function. That's something we can calculate. That's condition number 1. So if you want the power series to reproduce, if you want it to make a complete, clone of the function near the center of the series that you've picked a point where you're trying to approximate the function. I say approximate, but I should say reproduce because I mean this is exact, right? If I stopped before n goes to infinity, I'd have an approximation, right? Just like you guys had in 44, right? If you want to approximate the p equals 3 series, you stop. Yeah. It's just, g is like a given arbitrary function. Here, you could think of g of x being 1 minus x. And it just happens that by geometric series, we know we can write that equals to this. And so you can see the coefficients here are 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. But we're not always going to be able to do that, right? Like, for example, soon, right after I get done with this discussion, our next example we'll look at will be g of x equals to e to the x. Well, I can't rewrite e to the x as a geometric series. That's not a rational function, right? So I need something. If I want to understand how e to the x can be rewritten as a power series, as a Maclaurin series, I need to understand something different, right? Okay, so let's go on. what else has to match? If the function's values match at C, what else has to match at C? How about the derivative? What about g prime of C? That should also be equal to f prime of C, right? But what is f prime of x? It's a1 plus 2a2 times x minus c, right? Plus dot 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 plus n times a sub n times x minus c to the n minus 1 plus dot 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 dot. I haven't proved that. I'm not going to prove anything today. Today I'm going to give you plausibility arguments. All right? I'm going to show you how it works. I've proved enough this week. You've suffered enough. Let's just try to think about why things work today, and we'll worry about proofs some other day, okay? You're like, what you're doing right now feels like a proof. I'm fine. I don't know. It's hard to draw a line between what's proof and what's not proof. I don't know. But anyway, let me be more specific. I'm going to try not to worry too much about convergence today. Okay, so what happens when you plug in C to the derivative of the power series? A sub 1. So therefore, a sub 1 is equal to g prime of C. Don't get the wrong impression here. What happens when we look at f prime prime of x? That's 2a2 plus 3 times 2 times x minus c plus, let's see here, 4 times 3 times x minus c squared plus dot 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 plus n times n minus 1 times a sub n times x minus c to the n minus 2 plus dot dot dot. And I'm missing some coefficients here, right? Let me put those back in. This should have a what? It should have a sub 3 here, right? And there should be an a sub 4 here. So from this, what do we get? Continuing this thought process, let me number them. So point number 0, point number 1, point number 2 would be that g prime prime of C should be equal to what? F prime prime of C. But if you look at star, which is equal to what from star? Two times a sub 2, actually. Don't guess. Look at this thing. Plugging in, set. I'm sorry, you can't see. X equals to C in star. I'll get out of the way here in a second. See, everything that still has an x minus c power, 0. And all you're left with is the lowest order term, right? Did you guys see the pattern? What happens when we go to the third derivative? Of the power series, we got what? We've got 3 times 2 times a3 plus what? Stuff. And then eventually you get to n times n minus 1 times n minus 2. Am I to, that's 3 derivatives? Yeah, x minus c. Idiot. Not you guys, me. A sub n, x minus c to the n minus what? 3. That'd be the third derivative, right? So you can see that f prime prime of c is what? It's 3 times 2, right? A sub 3. So if we have g prime prime of c is equal to f prime 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 of c, that implies what? That implies that a sub, a sub 3 is equal to what? So that implies that g prime prime of c is equal to 3 times 2 a sub 3. In this one, we had what? 2 times a sub 2 is equal to g prime prime of c. So what do we get? At second order, we get what? We get, I need to box these in some kind of, I'll use red. So the A0 one was here. Here's the A1 condition. A2, what do we get? A2 is equal to g prime prime of c divided by 2. Over here, we have a sub 3 is equal to the third derivative, right, divided by 3 times 2. Right? The denominators here, can you recognize them as part of some pattern? Well, let's just try to do the nth one. Now that we've done enough, let's try to jump ahead here. What's the nth? What's a sub n going to be? Let me say a sub k. A sub k would be what? Looks to me like it's going to be the kth derivative, right? Evaluated at c divided by what? See what we had here? You could write this as the third derivative at c divided by 3 times 2 to see the pattern. See, third derivative puts 3 times 2. Second derivative, 2 times 1, right? First derivative had a 1, all right. So it looks to me like we can put k times k minus 1 times k minus 2 and so forth and so on. 3 times 2 times 1, right? Do you guys know a nicer way to write that? Indeed. So this is g, the kth derivative evaluated at c divided by k factorial. That is the kth derivative of g. That's right, yeah. So here's a definition. Given g of x, smooth, near x equals to c, the Taylor series for g of x is g of x generated at c is, here it is, f of x equals to sum k equals to 0 to infinity of g, the kth derivative of g, evaluated at c, divided by k factorial, times x minus c to the k full power. Smooth. Smooth. Smooth, what smooth means is that you can take arbitrarily many derivatives of the function, right? And all of those derivatives are continuous functions themselves. So what does Taylor's theorem say? Now I have the language I need to generate to state Taylor's theorem. Taylor's theorem says the following. And again, this is a rough statement of it. I'm going to worry about convergence. All right? Given nice g of x, we have g of x is equal to the sum k equals 0 to infinity of the kth derivative at c divided by k factorial times x minus c to the k power. In other words, let me put it into words. Taylor's theorem says that the Taylor series generated at C reproduces the function g of x near C. Is this at all surprising? Maybe. Let's try this theorem out on the exponential, okay? Like I promised. Let's calculate the Taylor series for the exponential centered at 0. Now, of course, I've stated this for g of x, right? But you could just as well take g and replace it with f everywhere here, right? In future lectures, I probably will almost always refer to the function f rather than the function g. The reason I referred to the function f versus the function g today was my starting point. I wanted us to think about f of x being a power series, right? Whereas I'm thinking about g of x being a series given by some other means. Excuse me, a function given by some other means, like the exponential function, right? We didn't define that as a power series, right? We defined it how? It's a function whose value is its slope every point or something like that, right? Okay, so then what? In other words, we're going to find the Maclaurin series. For the exponential. All right, so here we go. What's g of 0? Well, first of all, let me write it. I need to write a tower of derivatives. G of x is what? E to the x. What's g prime of x? E to the x. What's g prime prime of x? E to the x. What's g prime prime of x? G to the x. Okay, I think we get the idea. What's the kth derivative of x? G. Goodness gracious. Too excited. Still e to the x. What happens when you plug in 0? So, g of 0? 0, right? G prime of 0? 0? Oh, sadness.
1 all the way up.
Oh, yes, it is. I'm just getting this fixed, and then I'll go back and fix my... Hey, you guys are making corrections. I feel like, you guys ever seen that movie Awakenings? You know, he gives the patients this drug, and all of a sudden they start waking up from, they have, what do they have? Something that makes them kind of go into some sort of vegetative state. But then at some point they get this drug and then they start conversing with each other, and so I feel like that. Because usually I could say whatever kind of crazy nonsense I want in here many days, and you guys don't stop me at all. I could say something like, make America great again. We're going to make math bigger. We're going to make math better. We're going to solve the quartic. We're going to solve the quintic. Or we're going to take a manned mission to Jupiter. That's right, we'll show the Russians. I mean, ISIS. I don't know, whatever. A friend of mine says he now has a Trump hat. He's got one of those Make America Great Again hats. He'll take it out, and then he's got a spiel. He starts just to liven up his classes. He says that it goes over better. The more ridiculous you make the claim, the better the comedy lands. So he usually tries to work in manned missions to Jupiter and stuff like that. It's I like that. It's good. I'm still personally working on my various Trump-based comedy bits. Let's see here. So I feel like I've got about 8 years to work on it, though. So 9 years? 9 years? Yeah, okay. So what's the Taylor series for e to the x? The Taylor series for e to the x centered at 0 is 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed plus plus 1 over k factorial x to the k, and so forth and so on forever and ever. How do I know that? Where did those fractions come from? Come from the power rule, really. If you understand this motivation calculation, right? Every time we differentiate, we bring down a power, and those have to be reflected in the coefficients, right? If differentiating brings down power, and you want the coefficients to match the derivatives, then you have to divide by the same powers to kind of make it weight out. So that is, in fact, the Maclaurin series for the exponential. Question? Yep. There is something else to discuss here, right? What about 0? What's the 0th derivative? So some special cases, right? 0 factorial equals to 1. 1 factorial equals to 1. 2 factorial equals to 2 times 1, which is otherwise known as 2. 3 factorial, well, that's actually 6, right? And by the way, the 0th derivative at c is just f of c by definition, whereas the first derivative at c, of course, is f prime of c, et cetera, right? So this is 2 factorial. I could rewrite this, right? To be more explicit, 1 plus x plus 1/2 x squared plus 1 over 6x cubed plus 1 over 24 x to the 4th plus 1 over 120 x to the 5th plus 1 over 720 x to the 6th plus 1 over 5040 x to the 7th, and, well, that's all I know, but so forth. I mean, you can go as far as you want. And the further you go, the better polynomial approximation you have to the exponential near 0. Let me show you your first totally unjustified but super awesome example built over this. So, like, what would the Taylor series be for e to the x squared? Let me build off this example for just a second before I do anything much more convoluted. E to the x squared would have what Taylor series? I'd say this is like e to the u, right? With u equals to x squared. What's the Taylor series for u? I mean, the Maclaurin series for u. It's 1 plus u plus 1/2 u squared plus 1 over 3 factorial u cubed, and so forth, right? Which is what? 1. Right. Oh, one of the things I should have written over here, because I want to do it again over here, this we could rewrite more carefully in terms of sigma notation. Sum k equals 0 to infinity of x to the k over k factorial. That's it. I mean, that is the full. That's nothing different than what I wrote in the red or the blue, but it's a nice, concise way of stating it, the complete series, right? So how about e to the x squared? What would that be? Well, you can use substitution. In fact, that's valid. I haven't proved it, but so what? So, I mean, do you want to actually use Taylor's theorem directly to figure out the Maclaurin series for e to the x squared? Search your heart. The answer is no. Differentiate once, 2x e to the x squared. Differentiate twice, product rule. Differentiate thrice, 2 product rules. Differentiate, you see, I mean, well, it's always 2, I guess it's always just it's always product rules all the way down. Right? Differentiation, direct differentiation of that function is just a tedium. We could do it, but don't do it. Make a substitution. This is what, e to the, so x squared plus 1/2 x squared squared, right? In other words, you've got 1 plus x squared plus 1/2 x to the 4th plus 1 over 3 factorial x to the 6th, and so forth. Now, if you work at the other level of notation, this is the sum, k equals 0 to infinity, of x squared, parentheses, to the k power, divided by k factorial. So there's the Maclaurin series for e to the x squared. Guess what? How do you differentiate and integrate power series? I think I actually already used one of these things in my motivation over here. I claimed, what did I do here? I claimed you can differentiate a power series. How does it work? What did I do? I just differentiated term by term, right? I said the derivative of a power series is the series of its derivatives, term by term. Well, guess what? That's valid, as long as we stay in the domain of the power series. And you know what? The same is true for integration. You can integrate term by term for a power series just the same. So there's this term by term integration and differentiation theory. Check this out. What if I wanted to integrate e to the x squared? How would you do it? Well, you can't do it before today, right? E to the x squared does not allow an elementary antiderivative. But you know what you can do now? You trade e to the x squared for its Maclaurin series. Right? And then you use the term-by-term integration theorem, which really just says that you can pull the integral inside the sum. K factorial is a constant, right? So we just have the integral of x to the 2k dx. And of course, I have to add a constant because it's an integration, right? Now, the integration that I wrote inside the thing, I don't want to add constants there. I'm just thinking of that as just an antiderivative with zero constant. But this is not usually how the theorem is written. Usually the theorem just jumps straight. If you look at the theorem in the book, he'll just write what follows. He'll just write this. He'll just go straight to this, x to the k factorial, x to the 2k plus 1 over 2k plus 1. In other words, that what I write here see, to go from here to here is the theorem in the text. This is the term-by-term integration of power series theorem. What I wrote in the intermediate step is my intuition. That's how I think about the theorem. This intermediate step here is just intuition. By the way, switching integrations and sums and switching differentiations and sums is a dangerous game. That is begging a difficult and technical question about convergence, which, again, I'm trying not to get into today. But check it out. There's the integral. Right? And if you want me to write out what that series is, it's easier for me to go up here and just do it. It's x plus 1/3 x cubed plus 1 over 8 x to the, 1 over 10 x to the 5th plus 1 over, see here, 7 times, what's 3 factorial? It's, so 6 times 7, 42. It's everywhere. X to the 7th plus dot, 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 dot. And so since it goes plus dot, 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 usually we write the constant at the front. There you go. I mean, what's the line above is in some sense a better answer because it's a complete answer. What's below is in some sense a better answer because it's a more explicit answer. I don't know. What's that? Yep.
What happens with the k factorial 1 over k factorial?
It's right there. What do you mean what happened to it?
Well, I mean, like in the next step.
That's there. If you plug in k equals 0, let's see, what happens with k equals 0? 1 times 1, 1. K equals 1. 1 times 2 times 1 plus 1, 3. 3. K equals to 2. This is 2 times 5, 10. K equals to 3. 6 times 7, 42, and so forth, yeah. Which again is exactly the same thing as you get from just integrating this, then this, then this, then this, and so forth. Could you have done this without understanding convergence? You should say, yes, I could have done this without understanding convergence. You'd have good company, like Newton, Leibniz. A lot of the forefathers of calculus didn't really have a firm grasp on what convergence was. And mathematics sort of lingered in this indeterminate state of understanding of convergence for a couple hundred years, maybe. It was only the early 19th century that convergence, divergence stuff that we pinned down real careful before this lecture came to light, and it took the better part of several hundred years to really understand what the problem was. Because you can go an awful long ways with calculations like this, which seem reasonable, right? But there's a technical point, which is, anyway. So what other theorems, what other functions do we like that we'd like to learn the Maclaurin series for? Now that we've figured out the exponential, what's next? Oops. How about Kosh? So what's g prime of x? Cinch x, right? What's g prime prime? What's g prime 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 prime? G prime prime, sorry. 3 primes. Sorry. Okay, so basically you got a pattern here, which is that g, if we look at the 2j derivative, right, of x, we get what? Even ones come out to what? Kosh, right? But odd ones come out to Cinch. Agree? So what does this tell us? G, the even derivatives evaluated at 0 give me 1. And the odd derivatives evaluated at 0 give me 0. So what's the Maclaurin series then? How about this? The sum, j equals 0 to infinity, of 1 over 2j, parentheses factorial, x to the 2j. I'm going to erase. I think we have, I hope you have this, you're starting to internalize this. I'm going to erase it. Because I want to write another example here parallel to that one so we can look at it. So, okay. Let me just take a second here. What does this actually look like? This is 1 plus 1/2 x squared plus 1 over 4 factorial x to the 4th plus dot, 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 dot. Okay? That's it in detail. How about Cinch? So this time we get what? Like, by the same calculation essentially, what's the odd derivatives, right? Are Cinch, right? And the even derivatives are what? They're Cosh. Oh, I'm sorry. I got that exactly backwards, didn't I? Which derivative is this? That's the 0th derivative, right? Duh. I can't count. So let's fix that. The even derivatives are Cinch. The odd derivatives in this example are Cosh, right? So therefore what? G of an even derivative at 0 is equal to 0. G of an odd derivative evaluated at 0 is 1. So what? What's the power series for Cinch then? Using Taylor's theorem, setting aside our worries about convergence just for today, Cinch of x is what? It's the sum, j equals 0 to infinity, of 1 over 2j plus 1 factorial times x to the 2j plus 1. And if you write that out, what that is x plus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th plus dot, 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 dot. Let me remind you down here, e to the x was what? E to the x was 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th plus 1 over 5 factorial x to the 5th plus dot, 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 dot. How are these related? Right. Yeah, exactly. That is exactly, it's Cosh x plus Cinch x. But I can be more precise than that also. I mean, we knew that before, right? But also, you see the even terms in the exponential series are the Cosh series, right? The odd terms in the exponential series are the Cinch series. It all works together, right? But there's an observation we should make here while we're at it, which is that we should expect, all right, that a even function, all right, will have a Maclaurin series which only has non-trivial even terms. An odd function will have a Maclaurin series consisting of only non-trivial odd powers. See this? Cinch is odd, odd powers. Cosh is even, even powers. Not an accident. That will happen. Es bueno? How about cosine and sine? How would these examples have been slightly different with sine and cosine? Tell you what, what's that? They'd be alternating, right? Yeah, so like, let's see here. Now, so you could go through the corresponding calculations for sine and cosine, and maybe I'll do one of those tomorrow. But I'm going to do something slightly different since we have this in front of us. What's e to the ix? On the one hand, it's what? It's cosine of x plus I times the sine of x, right? If we remember what we did earlier. But there's another way you could go here, which is what? It's 1 plus ix plus ix squared over 2, right? Plus ix cubed over 3 factorial plus ix to the 4th over 4 factorial. I'll just go out to the 5th power, ix to the 5th over 5 factorial, like that, right? What happens when you take powers of I? What's like I squared? Minus 1, right? What's I cubed?
It's the other way around.
Negative I. What's I to the 4th? Is 1, right? I to the 5th is I again. So there's this, like, you know, it cycles every 4. So the point is, you can group this together. On the one hand, you've got 1 minus 1/2 x squared plus 1 over 4 factorial x to the 4th plus dot, 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 parentheses. And then the other terms you have there, right, are plus, I'll factor out an I. You've got x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th plus dot, 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 right? And water bottles aside, interesting drawing. Sec 150. Candy wrapper. Let's see here. I hope this isn't one of yours. It'll be embarrassing. Let's see here. No. Oh, this is a 128 person. All right. Hey, some of you were 128 persons once upon a time, right? Let's see here. So my point is, you could compare. This is, in fact, the power series for cosine. This, comparing, is the power series for sine. Of course, we don't have to derive these by this imaginary exponential jibber-jabber, right? We could also go through the corresponding differentiation, plugging in 0, and derive the Maclaurin series like that. Now, there's other things you can do, right? Like, what if you, for example, wanted to find, kind of building off this example, what if you wanted to do something like find Maclaurin series for f of x equals to x cubed sine of x squared. And I want to make sure I have about 10 more minutes to look at something with you guys, so I'm just going to kind of cut this example somewhat short. And I should put the projector down if I forget. What would you do there? What I would do, I guess the question is, do I want the whole thing? If I want the whole thing, then I guess I got to do this. This is like x cubed times the sum j equals 0 to infinity minus 1 to the j over 2j plus 1